pleasure to see you all here. We were kind of betting on 3 people or something like that in the first row, so it's really fantastic. My name is Jakob Rasmussen. I'm from a company called Apex Game Tools. Surprise, surprise. And I'll give a little introduction to what we do. But first of all, we have about an hour, and I think I will use about 3/4 of an hour to kind of show you some of the things we do related to next generation AI for Unity. I have some live demos today, so hopefully they will be better than some of the live demos yesterday. But you always know they can kind of fail in the middle of everything. But generally today I'll talk about some of the upcoming paradigms, and I'll show you some of the things we work with in that context. I would like to keep this a little interactive because I think 45 minutes of just me talking might kind of doesn't really animate. So if you have questions or if you have comments to any of the things I say today, just raise your hand, and we have a mic somewhere, and we can take them right away. And we also have 15 minutes approximately in the end for a Q&A, so you can also throw stuff there. And be open, if there's something you don't understand or something you want me to elaborate on, just shoot. First of all, I would like to know how many of you have actually worked with AI? Okay. How many of you know the concept of finite state machines? How many of you know the concept of behavior trees? How many of you know the concept of utility AI? How many of you know the concept of neural networks, genetic algorithms, neuroevolution? Okay, cool, man. Okay, so you can do the talk, Fantastic. Okay, so I'm going to take you through some of those things and give you an idea about kind of, the state of the industry today, what we see from the products we ship and from the customers we work with. So you might recognize a lot of these features, and hopefully there might also be something new that you can bring home. Okay. So, I'm sorry about the shitty PowerPoint, but I recently upgraded to Windows 10, and I'm a total nervous in that still. Okay, so basically, Apex Game Tools. So we have a couple of products on the asset store. The most well-known is probably Apex Path, which is a pathfinding tool for dynamic worlds. So kind of if your world changes a lot, that might be something you want to look at. Then we have a steering solution, which is for local avoidance and kind of formations and all this kind of cool stuff you see in AAA games. And then finally, we have an AI product out there, which is a utility AI, and I'll talk about what that is. It's the AI that had been used in some of the most popular games, like AI-wise, like Killzone and so on, which gives a lot of options of how you can do kind of poor man's fuzzy logic, and I'll get back to how that really works. I mean, basically, our mission is to try and take the Triple AAA, that's a lot of A's in one sentence, AAA AI, techniques and bring them to indie games, basically. So to make sure that you have, as an indie game developer, have access to the same fantastic technologies that you see in AAA games, but at a budget. So we kind of take knowledge from universities, we take knowledge from all these technologies and put them into packages that first of all work inside the Unity engine and also coded according to industrial standards. We have more than 20 years of experience in developing software, so that's kind of our take on this, right? And then we do a lot of research into these technologies, and that's what I'm going to share with you today. So, boom, boom, boom. What is the state of AI in games? I could just do that, right? Then we could kind of go in 5 minutes. Okay, so basically, if we look at what were the requirements of yesterday to games, right? Then as you know, the standard things about, AI should be easy to test. It should be easy to tweak, should be easy to extend, You should be able to implement specific use cases. So normally you would get use cases, for example, from game designers, and you would implement them, and when they worked, you were ready to ship. Often you have a budget, for example, 1 millisecond per frame. That is the maximum you want to use for AI, because the rest is probably going to be used, a lot of it for rendering, and there might be a lot of other things we want to run underneath the hood. So often you get a very strict budget, so it has to be very high performant, of course. And especially if you are running these kind of, RTSs or games where you have a lot of non-player characters that have to move around, that requires extremely high-performant algorithms to do that. And then also, normally AI has, a very short development time. I think it's changing a little. For example, the new Fortnite that is coming out, actually have quite a large AI team. I think it's about 4 game designers and 4 AI developers. But you will see in a lot of postmortems that AI is something that's thrown on the last minute, or when the rest of the game is finished, then you go in and then you do AI and so on and so forth. Of course, it can change a lot from kind of game project to game project. But those are some of the requirements we meet out in the field. Now, if we look at today's requirements, I think we're seeing a change in how AI is used in games. First of all, there is a kind of a new requirement for complexity. We want to do new things. We want to have the AI interact, for example, with the player, or we want to use AI for, animating the world, from this kind of director logic to other logics that sort of, keeps the player excited. We want perhaps AI that speaks or comprehends, what the player says or writes and so on. Or we want to have worlds where NPCs are much more kind of vivid or alive or much more natural in their behavior. So we can kind of animate the worlds much like a movie where you see it. But also there are other things. When AI gets complex, we cannot just design it based on use cases. It's simply not enough. You get all these kind of videos on YouTube of stupid AI and AI that runs into walls and so on. So you need to give it more fidelity. So you want AI that learned by examples, you want AI that can also do unexpected behaviors, especially in scenarios that we didn't foresee, that we actually want the AI to adapt to this. We want the AI to also be able to take decisions in use cases that we didn't specify, because we simply don't have the time or the brain power to specify all use cases. And then, of course, as games become bigger and we want more fidelity, there is also a demand for even more performance. So you see, for example, that the GPU is increasingly used for AI. We are throwing a lot of stuff at the GPU because suddenly we have access to a completely order of magnitude more power for doing stuff. And in order to have game worlds with 1,000 or 10,000 agents running on a regular device, those are some of the technologies that we want to use. So we're trying to kind of push AI into other technical dimensions that have normally been reserved for other high-performance requirements like rendering and stuff like that. And then, of course, we also see a completely new field of AI opening up, and that is, we can use AI that comes from industrial applications in games for analyzing data. Either, monetization and so on, but we can also use it for optimizing player experience or for, managing difficulty levels or for our understanding. We saw yesterday, for example, where then you could kind of analyze a level and find out where do the levels actually break down when we work with players, and we can actually use AI to do that. And we can even use it to generate levels or to change levels so they actually adapt to the game in itself. And all these technologies are becoming available. And, one of the reasons why we started looking into that was actually, when I started, going into computers as a kid, I always saw these amazing graphics, and I saw how the graphics industry was almost being pushed by the game industry and the requirements for games, right? And we kind of saw that even the GPUs that are being shipped, for PCs and primarily for the game industries, are now actually the foundation for training these deep learning networks. So they're actually foundation for other industrial applications. But we haven't really seen kind of the same tendency as rendering had to, where computer games were state of the art. We haven't seen that yet in AI, And games is kind of the perfect simulation of the real world. So why don't we use games to actually kind of extend the state of the art of AI as well? And that's kind of one of the things that motivates us to go into this field and say, look, we can use games for this. We have, millions of players around the world, billions of players even, massive amounts of data. We can make amazing things with AI in games, and we have these huge, development communities of extremely creative, pragmatic and skilled people. So we can do amazing things with AI in the game industry, and that can then transcend out to the other industrial areas like, pharmaceuticals or whatever, instead of the other way around. Okay. So, however, these are kind of, the requirements for the industry in general. Now, of course, a lot of us are developing indie games. And for indie games, there are some additional challenges that we have to manage. First of all, the average indie team is not likely to have a skilled AI programmer or someone with deep knowledge of algorithms or mathematics on the team. So that's a challenge. And that's one of the reasons why often you don't want to start out as an indie game company to making your own frameworks, because you're probably going to use up all your budget just kind of making your behavior tree framework or understanding how neural networks they work, right? You have a short time frame, meaning that you might not even have the time to do this. If you want to ship within 3 months or 6 months before your budget runs out, to get some money into the company or to ship your first game, you don't have the time to build the tools first. You need them from the onset, so you can just make your AI and make your game quick. And you also need time, for doing other things, right? Have a small budget, meaning that you cannot buy this from the outside. You can't buy a $40,000 AI framework, or you probably can't afford a kind of highly skilled senior AI programmer because he's probably hired by, the biotech industry or something like that, so he's not going to work on your indie game for you. And then there's also a fourth thing which is very important, that indie games, in a way, tend to be more creative. So often what you want there is that, you want to go beyond the state of the art. You don't want to just copy AAA games with kind of worse graphics, right? You want to do new things. You want to have creatures that interact with the player in different ways, and you have all these crazy ideas. So actually, in some cases, the indie games are pushing the curve for AI because they're much more creative. They're much more unrestrained. And those are you guys, right? So all of this coming together, there's a need for these tools and the knowledge, how to implement them, how to use them to be available, so you can kind of expand on your ideas, right? And unfortunately, we see a lot of games that kind of want to do amazing things, but they stall in that process because they don't have the technology and they don't have the knowledge available. But they have fantastic ideas, right? So the idea is, how can we make those technologies and that knowledge available so you can, as quickly as possible, go from idea to real game, and then concentrate on all the magic stuff like storytelling and, the graphics and the interaction and so on and so forth, right? So, this is basically the playing field, you can say. When we look at different technologies for AI, we have kind of from one end, we have the controllability, right? If you're doing simple things where you need 100% control of what's happening, finite state machines and animation technology, we're going to patrol. He shouldn't do crazy things. He's patrolling from A to B or something like that, right? But once they become a little more complex, your use case, your scenarios, there is this technology called behavior trees, which is basically, you can say, an extension of the finite state machine in a tree-like structure that enables you to have more complex AIs running, right? Then what happens is that, the less control you need, but the more complexity you need in your AI. And these AIs very quickly get big. I mean, there are on Gamma Sutra, there's postmortems of finite state machines with kind of 400 or 500 states in AAA games. And I can tell you they're impossible to debug, and you need a really large team working on them to kind of maintaining them. So at some point when AIs become more complex, these technologies simply don't cut it anymore. So in the middle here, we have a kind of utility AI, which, there are some very good examples of how this has been implemented in games, which kind of, and I'll go into how that works, which kind of give you the ability to introduce some fuzzy logic, to say, look, we cannot map out all use cases, so actually we're going to introduce some ways of taking decisions that are not necessarily inherent in the use cases that we have, but it can kind of interpolate between different decisions. And then, of course, comes some of the really, really cutting-edge technologies here. I mean, neural networks as such is not cutting-edge. We've been working with them in the 70s and 80s. But funnily enough, it took kind of 20 years to solve a lot of the problems. So we just now see with kind of deep learning and Google and Facebook and everyone on the planet going into this, that neural networks actually become really, really useful beyond the insurance industry. And then out here, we have some of the really crazy technologies. And I'll show you some examples today. Neural evolution. And neural evolution is basically the next step after neural networks. And instead of designing the network, we let the brains grow themselves, just like we grow brains in ourselves and in creatures, right? And that gives some amazing possibilities, some of which includes new ideas, creativity in the machine. That the strategies the machine will come up with is not something we necessarily designed. And I'll show you what some of the ideas that could be used for and how it actually works. Okay, any questions so far? Just shoot, right? So, look, you're lying, I don't believe you. Okay, so this is an example, that I've taken from I think it was a postmortem. We used to have a behavior tree running and everything was running fine until I tried expanding the system for more complex behaviors. The behavior trees were getting huge. Have any of you with behavior trees experienced that? Massive behavior trees? Harder to maintain, and some performance issues started to creep up. Have you experienced that? Yeah, some of you have. This is a challenge, right? I see a lot of projects where you start with an AI and think that's easy. And then suddenly you realize there's so many corner cases. There's so many things we take into consideration. Suddenly it doesn't realize there's a column in front of it, or it starts shooting at the player when it shouldn't do, and so on. And suddenly these AIs, and especially if you want to have some kind of natural behavior, they become massive. So you need technologies that can kind of harness that complexity. And then, I looked at an alternative and stumbled across utility theory. So one of the things when we started looking into kind of a high-level decision-making frameworks was that we looked through all the postmortems. We interviewed a lot of companies, and we kind of looked at what kind of AI actually gives, possibilities for harnessing some of that complexity. And this kind of idea about utility theory came up, and I'll show you that. There are not many games using it yet, but there might be a few that, when you kind of look into it, for example, beyond the Killzone series, as I said, Civilization is using it for their AI. And there's a few other games out there that use this. So what is utility? Well, utility is basically the idea that instead of designing the AI and kind of saying, look, if this happens, you should do that, and this happens, you should do that, like you do in a behavior tree, you turn it around and you say, look, we need to start with a goal. We need to say, what are you trying to achieve? And depending on what the context, the world around you, how that looks, what is the usefulness of doing certain things? So in this case, we have a simple, that could be a simple first-person shooter, where we say, look, we can do three things, right? We can fire, we can load, or we can take cover. This is a very simple case, but it's actually a very common problem in computer games. When you look at it on the face of it, it's easy. It's like, look, it's very easy. If the enemy is there, I'm going to fire, right? If I'm out of bullets, I'm going to reload, and if I'm under heavy fire, whatever, I'm going to take cover. But then the problems start creeping in, right? You start saying, well, what if I only have 3 bullets left? Should I reload, or should I shoot? What if there are 4 enemies approaching with 3 bullets? They're far away. Should I reload now and then shoot all of them, or should I try and get 3 of them, and then the last one is probably going to kill me while I'm fiddling with my magazine, right? Suddenly you realize that all these kind of complexities that open up, and you can't harness them in a behavior tree, right? It doesn't work. You need more powerful AI. One thing you can do is that you can actually go in and say, well, if there are so many conditions for why I should fire, why don't I put them in there and say, all these reasons is why I should fire? And then you put in all these reasons, this is why I should reload, and all these reasons is why I should cover. Seek cover. And then suddenly you get a kind of decision landscape that is much bigger, and where you can actually put a lot of different, scenarios or use cases in that you probably hadn't thought of. And I'll show you how that works. I'll take an example where we look at human desires, right? A typical use case, you come into a game design and say, oh, I have this amazing idea, man. We're going to make a game where people are going to run around in an apartment and they're going to do all kind of crazy stuff. Wait a minute. No, it's completely new. Okay, so what are we supposed to do, right? And you might have seen this scenario before as AI programmers. You get this crazy thing, right? Well, if I have energy, I will work, except if I'm hungry. And already, okay, shit, wait a minute, There's a condition here, and how does that work? And however, if I'm very sleepy, I will sleep unless my hunger is extreme. And you can see how it kind of goes on, right? It becomes more complex. So, but if my sleep is extreme, I will sleep first. But of course, if I need to go to the toilet really bad, I'll do that. And this, however, should come rather urgent. And you see all these kind of natural language expressions, right? They don't map into a kind of, states and conditions and so on and so forth. So you want a tool where you can kind of harness that natural language and implement it directly into an AI and have it running and showing very quickly the game designer, is this what you want? Is this behavior you want, right? What the game designer really means, and we have the whole table here, is actually that, you have a lot of conditions, right? About how tired am I? When was the last time I went to the loo? And, when was the last time I had my meal? And giving a lot of those conditions, there is a utility to, should I sleep? Or should I go to the loo? Or should I eat first? So on and so forth. And what the game designer really means is that, look, depending on all these different scenarios, I should do different actions. And we can actually map that out together with the game designer. But we can do something that's even more beautiful. In the old way, you would do something like this, if, then, and make states, and, suddenly they would break because you forgot a condition or you're lost in some state like this. Or even before state machine, you might implement it in script. I mean, I've implemented a lot of AI scripts. But what you can do, of course, you can say, look, don't worry, we're just going to make some nice curves, right? we're going to have a curve here and say, look, energy, most of us probably during the day, we have high energy in the morning. Or do we? Do we have high energy? I can see some of you don't. But most have, But normally we start with a lot of energy, and then when it's kind of close to, night, we're going to, fall asleep over the computer game or the TV or whatever, and then kind of wake up next morning. Hunger is very different, right? That's not during the day. That's actually a completely different input dimension. That's kind of, when did I last eat, right? Then my hunger kind of, I can always eat a little, right? I can always snack a little, but then when there's, a long time has gone since I was eating, suddenly my hunger actually become quite massive, right? And then I really want to have something to eat. The sleepiness is probably something like this, right? Most of the day it's okay. We can take a nap here. We have nothing else to do. But otherwise, suddenly we get very, very tired, and then we're going to go to bed. And then, of course, the bladder is something completely different, right? I just went to the loo here, it's all good, and suddenly, hey, well, wait a minute, I'm about to speak, and then kind of, in the middle of the session, I have to run out. Now, the magic here is that we can compare apples and pears, right? We can actually take different inputs and put this into the curves. In this case, they're all kind of time-related, but basically it could be anything. And then we're going to normalize that to a value from 0 to 100, and then we can sit together with the game designer and say, look, is this what you want? Right? If, it's 3 hours since I ate my last meal and it's the middle of the day, what am I supposed to do? Should I keep on working or should I go to lunch? Well, probably, here, my hunger is so high that, it makes sense that I go to lunch, right? But if I ate a couple of hours ago and I still have a lot of energy, I'm probably just going to take it easy. And in that way, you can suddenly design AIs directly together with the game designer, expressing this in natural language. And the magic of it is that even a lot of the use cases that we didn't foresee will be handled here. What happens if, I'm actually, it's really pressing, but I'm actually also very hungry. Well, then I will eat first. But we didn't necessarily map that out. And you can use that for anything. I took desires here, but we can use it for the FPS shooter. We can use it for strategic decision making, giving orders, anything that can be put into this framework by taking input, normalizing it, making these curves, and seeing, choosing the output with the highest value, the highest utility, is a way we can solve that. And we've implemented, crazy complex AIs doing this. And I'll give you some additional examples of how this principle works. Tactical reasoning, right? This is a classic problem. You have some kind of game where you need tactical reasoning. Whether this is a football game or it's a tactical shooter or it's an FPS game, you want the AI to have an idea about, look, where should I be to optimize my position, to either receive the ball or to shoot the enemy or to make sure that the player doesn't get through. And this ties to something which is very complex to do with traditional AI technologies, which is spatial reasoning, right? Because you can basically have an infinite number of positions in the game level, and you want to pick the best one, because you can only be in one place unless you're some kind of, superposition quark. One way you can do this, and I'll show you, we have implemented this in a demo that's available on the asset store. One way you can do this is simply to say, look, we're going to take all the positions available, and then we're going to score them with utility functions. We're going to do things like, look, are there any of these positions that are in cover? Are there any of these positions where we have a line of fire to the enemy? This is the exact same way the Killzone 2 AI was implemented, and it actually gives very good tactical reasoning, because you basically score all the positions that are available, and then you pick the best one, and that's where the little guy is going to run. And I can show you here how that works in real life. Can you all see? Should it be bigger? It's okay? Okay. Inside Unity, live demo. Let's see if it works. Here we have our little fellow. So we've animated him with an utility AI, and he will be shooting the zombie teddies. And you can see his tactical reasoning here. So basically, the green numbers here are positions just in the vicinity of him that will score based on a number of principles, like which one is closest to him, where can he actually see a teddy, which one is in a certain distance to a teddy, so he will kind of be in nice shooting range, but it shouldn't be too far, right? Simulating that he has an accuracy. Which one has actually a line of sight to a teddy? If there are multiple teddies, he will kind of try and take a position that is outside of their half planes, so he won't get surrounded by them. And in that way, he can run around forever. And the other thing you might also notice when he's moving is that it actually looks like a human. I mean, it might not be perfectly like a human, and there might be a few areas where you say, look, you should extend the AI here. But actually, he seems kind of moving naturally, to a pretty good position and so on. And the thing, of course, here is that there might be cases where there are no optimal positions. And that's the beauty of utility AI, because we can't guarantee he'll find an optimal position, but we can guarantee that he will find a pretty good position given the circumstances. And that principle you can basically use across all decision-making processes, choosing between strategies, choosing what power-up to take and so on and so forth, can all be put into a utility-based framework. Yeah. Should we have a microphone? Sorry, we're just getting a microphone because we also have a video running.
Hi. I'm having a question regarding the numbers.
Yeah.
Because I'm seeing the puppet going to a certain direction when the numbers are limited to a kind of a rectangle. But outside of the rectangle, the danger exists. So.
Yeah. Well, I mean, currently here we just sample this rectangle for him, so that those are the positions that we allow him to go to, and we only score among them. And
Okay.
and you can say, there can be many considerations for this, right? One of them can be performance. That if you want to sample the whole world, and if you have 1,000 agents running, and you have a number of criteria, you can get into performance problems, right? So sometimes you want to limit the selection process to make it really efficient. But for this, it's also about demonstration purposes, that we can kind of show, look, these are the positions we evaluate, and they're kind of easier to look at, right? Okay. But it also, I mean, it's a very good point, because it also shows you the value of visual debugging, which is so important when you do AI, right? You can color code these, so you can actually have kind of heat maps, where should he go, and you can also cut off, we call them scorers, that we kind of score each position with a number of scoring functions, and you can take them off one by one, so you can actually debug them individually and say, look, the half planes that you get him out of enemy's reach, okay, they score like this. The cone of arc of fire, for example, that we prioritize should look like this. And in that way, you can actually build your AI step by step, knowing it's almost like a visual unit test, right? You know that each function actually returns what it's supposed to do, and then subsequently, when you tie them together, you have the overall decision-making, matrix that this AI has.
Okay, that was my question.
Yeah, thank you. Yeah, there's another question down here.
Sorry to make you run there. So my question, I guess, is about using utility to describe imperfect behaviors. So let's say I want to design this character to be really good at avoiding enemies, but then when it comes to a ranged attack, maybe he's slightly worse at dodging those kind of things. So does utility work in that? Could you sort of apply it in the same way as you've described to things like imperfect behavior?
Absolutely. I mean, this is actually one of the very interesting aspects, because you can use the scores to instill personalities in the AIs. So you can have two AIs that basically use the same AI by design, but by changing the scores that you assign, you can actually have different behavior. So you can, for example, have an AI where you say, well, look, this scoring function that kind of takes him away from the teddies, you're either going to remove that or you're going to reduce that to a very low range, meaning that the AI will only start moving when the teddies are within 2 meters instead of 5 meters, for example. That will give you a much more aggressive behavior or much more stupid behavior, depending on you have a gun or not, right? So in that way, you can actually, using the same framework, have very different personalities in your game. And you can even randomize them procedurally on setup, so you can kind of generate all kinds of personalities. So if you want to have a little variation in your squad or between your soldiers or your adversaries, you can actually do that. And the thing is also, it's kind of easy to do, because you can clearly see and you can debug it visually, what are the scores that are active for this particular AI that's in motion or that's moving now. And we're actually using that in a number of games to install different personalities and to have different behavior during, for example, space combat or something like that among enemies. But it's the same AI you go to, so you understand how it works. You don't have to have a lot of kind of different trees running around. You just modify the scores to kind of simulate that. Thanks. Yeah, there's another question up here.
Yeah, I was wondering, can scores influence each other? For example, if you have a certain reload time, and you can't move during reloading or something.
Absolutely. Yeah.
Does it mean you kind of iterate through the values, see which influence what in that frame, and see how long the...
Yeah, I mean, theoretically they can. In reality, we haven't come across many use cases where you want to do that. But we have some use cases where what you want to do is that you want to sample, for example, all the scores, and only if they are above a certain threshold you want to move there. Let's say, for example, you want to move to a cover, but you only want to move to a cover if it's good enough. And then what you do is that you sample all covers in the vicinity of the AI, you return them, and only if they score above 100, for example, you're going to run to cover. Because if it's kind of cardboard boxes or oil cans or stuff like that that you can shoot through, you're not going to take it. But if it's a concrete wall, you want to use that cover, for example. And then you can use a utility AI to kind of calculate, arc of fire, and is this exposed to an enemy and stuff like that. And then only take the covers that are relevant. And then feed that back into another AI. But the particular problem you describe is also about interdependencies between AIs. And normally what you want to do is that actually you want to have multiple AIs running in parallel to have separation of concerns. So you can, for example, have one AI that will constantly be updating, look, do I need to reload, for example, right? And then if I need to reload, you can have another AI saying, okay, so when should I do it? Should I actually do it now? You often use that in targeting, where you say you have one AI running targeting, completely separate of everything else. Just kind of hammer out targets. And whenever you want to shoot, you just pick that target. It gives you two advantages. First of all, your AIs become very simple. And the second challenge is, or the second advantage is, that you don't have to run the shooting AI if you don't have a target. So in that way, you have separation of concerns, you have simpler AIs, and you use this advantage. You can actually run them in parallel to constantly evaluate, look, what I'm doing, is it good, and so on. And in that way, you can handle interdependencies. You then communicate between the AIs using a memory. We call it a context, but it's basically the AI's memory, where it will kind of store all data and use that to exchange with the different AIs. And sometimes we can have 20, 30 AIs running in parallel to simulate complex behavior in a character. And it works really well. It's very easy to debug, and it's very easy to get an overview about how does this AI work. And the third advantage you get is that your AIs become modular, so you can reuse them. You can say, look, this targeting AI, we're going to throw at all AIs that needs to acquire a target. So you don't have to kind of add branches to trees or stuff like that. It's just modular, and you can shift them around. Right? What, sorry? Yeah, so we have 3 AIs running on this guy. We have I can just show you, it's exposed in a component here. I don't know how much you can see, but basically you have I mean, it's grayed out a little, but you have a scanner, so it constantly scans its environments for power-ups and enemies and stuff like that. So in that way, we can also control how often do we want to run that, so we can adjust it for performance reasons, for example, if you have a lot of AIs running in the same scene. We have one AI that chooses the action, choose should he shoot, or should he reload, or should he pick a power-up, or should he throw a bomb. And then we have a third AI that controls the movement. And that means that, he moves and does actions at the same time in parallel. Just like our brain works, right? We have multiple faculties that will do all kind of crazy stuff in parallel. And you can just extend that. You can also have one that, for example, chooses a strategy for him, an offensive or defensive strategy, for example. You can have another AI that gives orders to his teammates that might be around him if you have a small squad. And they can all be separate and running at the same time in one character. And you can, go in and debug them separately. So you can just see the editor here where this is a movement AI. Come up here. I don't know if you can see it that well, but basically you have 2 nodes here, and that's it to do it. And basically the first node is, look, if you have an enemy, move, and the second node then decides where to move. And where all the magic happens is down here in the, it's down here in the move to best destination behavior. And what you can see out here, I mean, I know you can't see it, but you can always come by a booth and you can download the demo if you want to. And then over here we have all the different scoring functions that actually scores each of these positions and show where he's going to move to. And that's basically how you build these utility AIs, right? And the advantage you get is that it's quite modular and kind of easy to extend them. Okay, cool. Were there other questions? Oh, there's another question down there. Yeah?
So what if you have to work with multiple agents that have to cooperate, and then one agent's decision should influence the other agent, but then it really depends on the priority between the two agents. Let's say if one agent moves, then it's better to stick together, so the other needs to move instead of shooting.
Yeah.
But if then the other sees an enemy that the first doesn't see, then this changes. How do they then intercommunicate?
Yeah, this is cool. So this is a very cool scenario. So there are a number of ways to solve that, and it depends a little on your game, right? In some games, you want to have a blackboard where they share memory, like in RTS, where you want all units to react to the same information. It's kind of a little boring because everyone has access to the kind of hive mind, right? But it's often how it's implemented. Another way you can do this is actually that each agent has a separate understanding of the world, a separate construction of the world. And then what you do is that you let them communicate. And in that way, you can also control the communication. You can say, for example, you can only communicate if they're within 30 meters and line of sight, if they don't have intercom or some other magic, right? And they can also have different perceptions of the world. So, one of them might have seen that the bad guy has died, the other one might not, so he's still kind of walking around there with a wrong view of the world, but will be acting according to that. And then what you do is that you communicate, for example, either through messages or through orders or something like that. For example, if you have a command and control hierarchy in a kind of military tactical situation, you might get an order from your boss depending on kind of his view of the world. And then you can either choose to implement that, he will say charge, but you can see a guy out there that he doesn't see and say, look, I'm not going to charge out and get shot by this guy, right? So you're actually going to override that order because you have other information. And you implement that behavior in the AI. And the magic about that is that you implement it just like I explained it here, right? So when you look at the AI, it's like, look, I have an order which is attack, but I can see an enemy, so I'm going to evaluate how dangerous is this guy. And if the enemy scores above 50 in the, kind of points, I'm going to stay here and try and take him out first. But if not, I'm actually going to take the chance and run, for example. And in that way, you can get this kind of natural coordinated movement between the agents that looks perfectly natural and that has been explained just like I do here in natural language and implemented in the AI. And you can debug and you can say, okay, why is this guy not moving? Well, he actually sees another enemy and he evaluates, the threat is too high, it's too dangerous for him. So he'd rather take the repercussions of not following an order. And we actually have demos. There is a Gamescom demo that we implemented for the Mandate where they have this kind of tactical combat and you have body teams moving around, communicating with each other, sharing information, not having full information, making all kind of military maneuvers based on kind of Russian military doctrine and so on. It's quite amazing. And you can do that very easily. And what you do, of course, is that you use this kind of power of having a memory and then being able to pull information from that memory and use it in the AI, and then having the different agents communicate with each other. Answer the question? Okay, otherwise you just come by and we can keep discussing. Cool, okay. So I give you a few more examples. Tactical reasoning. Yeah, so these were the some of the examples. So another example, dynamic dialogue. There are many games where we actually want to have the dialogue by NPCs is based on context, right? We are kind of level 1000, demon warrior with a mighty sword. We don't want to be offered a small rusty dagger when we come to the shop, right? We want to be offered something that actually is relevant for us. And you can use the utility AI to kind of make this kind of dynamic dialogue. In this case, we have a shop, where we have 3 categories. We have the type of item we're offering, is it healing, a weapon, or armor? We have the quality offer, is it low or high quality or something in between? And finally, we have the price. And all these parameters that the shopkeeper, who's run by an AI, is going to offer the player will be based on utility. And we might want to use a lot of different dimensions, right? This could be kind of based on what is the player's current health, If it's low, we might want to offer him, as a good salesman, we are a health item rather than a weapon, right? But it could also be other things, For example, the price we offer could be based on what is the reputation with the merchant, right? I mean, if we're an evil guy that walks around and kills villagers, we might say, look, I'm going to charge you a fairly high price for that magic sword because you're probably going to use it on my neighbor or something like that. So the interesting thing is also here that the input dimensions can be very different. And you can basically just invent them, add them with a scorer, and add them to the AI without having to remodify the AI, which is kind of magic. So let's see how this works in practice. Again, you can use points like you did in a tactical positioning demo, or you can have curves as here, for example. One example could be here, you know, that for healing items, you know, if you have low health, you know, if you're not very wounded, we're not going to offer you healing items, but very quickly, if you just have, you know, some kind of severe wounds, we're actually going to offer you, or the merchant is going to offer you a healing item, right? When it comes to weapons, then you can say, you know, based on kind of what level you have, for example, that is going to depend, or for example, how much money you have, that's going to kind of influence whether we offer weapons and something similar to armor. I just want to get to showing you the example. And you can do the same, you know, for quality offered, kind of say when do we offer, you know, low quality, when do we offer medium quality or high quality, and that, for example, can be based on how much money you have. And if you have a lot of money, or if you have a very special reputation, then, you know, perhaps you get offered the really, really high quality special magic item, right? So let's see how this works out in practice, right? So we have a repository of dialogues we can add to it, or we can use natural language for that matter. And then, you know, it's very simple, right? You know, if we have a kind of low quality level item, we can say, look, you know, an iron axe is just what you need. It's a little one, but capable of a good blow, right? If we're actually offering a medium quality item, we can say, look, a fine, and then just add a steel sword. And all this is based on how we actually score the relationship between the merchant and the player. And so on and so forth. And, you know, if it's a high quality item, you know, this mithril axe or whatever is the finest weapon in my shop. Or, you know, if it's a special item, it can be the sword of the Titans, right? So different dialogues hard-coded in. And we put that together then in a dialogue, right? So you come in and you get this kind of, you know, random greeting, what a fine day today. He looks at you and he can see, okay, these guys need weaponry, so he kind of pulls one of the sentences there, you know, you need better weaponry, or, you know, your weapons look worn, or I can offer you some special, you know, for your aggressiveness. And then he just adds the sentences, you know, an iron axe is just what you need, and so on and so forth. And for a person of your fortune, because the player has a lot of money, he will say, look, I'm going to charge you a high price. Very simple. And the thing, of course, is that then you can just kind of add additional dialogue, add additional items, and add additional scores, and this can become more and more complex, so you'd never really repeat yourself inside the game. So, example 4, dynamic worlds. And I'm showing you these different examples also to give you an idea about, we are basically using the same concept of utility to solve a lot of problems within AI, which also means that we only have to master one technique to do design-based AI, because we can solve almost any problem that we have. We can even do formations, you know. Normally you would use kind of, you know, advanced mathematics, but you can actually use utility AI to do formations even in games, right? So it's kind of one tool for many purposes. And that, of course, gives the advantage that we're going to master it more quickly, that everybody knows where to go and look for things, that we can use the same development tools. You know, we only need one editor. We don't need one for the state machine and one for the behavior tree and one for the, you know, whatever. It's the same tool and the same technique, and everybody understands how this works. So this is going to be the final example of utility AI, and then we're going to move on to the other things before we run out of time. So normally how you do worlds in many cases is that you script them, right? You say, look, you know, this is what's going to happen. We have a line of missions and so on and so forth, which is fantastic because you can make a very kind of bespoke storyline. You can have, you know, a lot of dialogue that is tailor-made to it, and you can have all these plot lines that weave into each other, right? Some of the challenges, of course, are that you have to make all of them. You know, you have to write. You need a story writer to actually write all of them. The second problem is also that they might be out of context. When you actually get to slay whatever, the evil witch, you know, you're already level 100, so you're like, hey man, I mean, I fix this pretty easily, right? Or if you kind of fall out with the Red King and suddenly the Red King offers you a quest. And these kind of things, right? Most of us already know them. And of course, the second challenge is replayability, you know? I saw a presentation about Steam that, you know, some of the games that fail on Steam are the ones that are story-based in early access, because how are you going to go through a story twice and kind of find it intriguing, for example? So there you actually want to have some replayability where you can kind of create stories dynamically, and they have to be good, right? So, of course, you can use a utility AI to do this by actually creating an ecosystem. And you use the utility AIs to animate the different AIs and make the different events that you want to happen. So they're not going to be random. They're going to be a reason behind all of them, right? Of course, the chances are that if you don't make these algorithms kind of, you know, complex enough, they will start repeating themselves. But let's see how that could happen. In this case, and I've just made a very, very simple example where we actually implemented this in a game in a more complex form. In this case, we have a star system, for example, or you can have cities or whatever. And the interesting thing is that we have two factions, and they actually each have an exposed system, right? So you say, okay, what are we going to use that information for? Well, we can use that information to a lot, right? Because depending on what the faction is, they can actually go in and via utility scores evaluate, so which of my systems are exposed, right? Where don't I have enough military? Where's there a chance that you know, the other faction can actually strike me? This is basically using an old technique called influence maps, where you can kind of do strategic reasoning in grids or in other spatial structures like a mesh here. And basically we're using utility-based scores to get an idea about where are the problems. And it can also be that, you know, a certain world has symbolic importance and so on and so forth. And then we can have different personalities, as I mentioned before, right? So depending on what type of faction you are, you might either call the player and say, look, the enemy has an exposed faction, let's attack it. You know, do you want to help us attacking the system? And there you're generating a mission on the fly based on what is really happening in the world, right? If it's a defensive faction, they might come and say, look, will you help us protect our system? We can see it's exposed. We don't have the military to go there. So, you know, we are offering you a mission and we are offering you a reward for this, right? And suddenly you have, you know, with no scripting, you suddenly have dynamic missions that actually make sense in the world. And you can see how you can extend that. And then, of course, you can go further. Because depending on whether the player kind of sided with the aggressive side or with the more passive side, they might bear grudges. They might remember what the player did. And suddenly you have a complete unique story to that game that unfolds, right? Where the kind of, you know, if the player didn't actually honor the aggressive mission, you know, they will say, look, man, we didn't forget. You didn't help us when we attacked that system, right? Or the defensive side will say, look, you know, you didn't help us protect our system. So suddenly the player is you know, immersed in an ecosystem that automatically kind of generate these missions. And, you know, you can go anywhere with this, right? I think I have a list here of all the kind of crazy things. So you can take a picture of this, or you probably get it from the side, of all the kind of crazy things you can do with these kind of dynamic storylines, right? They just automatically generate the quests. And they all make sense. And they're not boring or repetitive because they can be based on actual faction personalities or AI personalities that have kind of different views of the world. So if you are an aggressive, you know, hardliner, you can go with them. If you're passive and want to protect the weak, you can go with them, right? Okay, so in the final part of the presentation, I'm going to go into these kind of two last bits concerning machine learning. Now, there are cases where we actually don't want to design our AI, where the world is simply too complex to put that into a design-based tool. And in that case, machine learning offers a lot of technologies to help do that. And a simple example could be, I think you know all of this, right? Neurons and this kind of stuff, so I'm not going to go through it. I'm going to skip right to this. Basically, the numbers I showed you before in the utility eye where we use the curves, we can use them as examples that we throw into a neural network instead. So basically anything that these AIs, they do on design time, we can actually have a machine do instead using neural networks. Now the disadvantage of that is that we cannot guarantee the kind of the same smooth curve when we actually have networks training. So the problem is that, you know, if the data set is very large, we get an interpolation, but we cannot control it. We cannot look inside the machine. So in that case, you actually, if you know you have a use case, you don't suddenly want to see kind of crazy behavior from your AI. You want to use these kind of design-based AIs, where kind of the last installment so far we have seen working is utility AI. But you can actually do the exact same thing with a neural network. However, there are a number of challenges that you have to be aware of. So we see a lot of indie gamers that kind of start out by saying, look, I'm just going to throw in a neural network and it's going to make magic things. And that doesn't happen. You know, that's kind of the thing you should go for if it's really a last resort, or if you have a very special case, or you know neural networks very very good. And some of the challenges are, of course, that you have to set your hyperparameters. You have to understand how big should the network be. There are an example, for example, Supreme Commander 2. Have you seen the AI for that? Any of you familiar with that? So they actually used a neural network to train that, and that meant that whatever they did in iteration, it took about an hour to retrain the AI to respond to enemies. And it's one of the examples I know of really good use of neural networks in actually making AIs. But you have to understand what you put in to the networks? What are the kind of the inputs that you sample and then use that to train the network on? Then the challenge can also be that they can take a long time to train. You know, in Supreme Commander 2, they actually use very small networks, which I would definitely advise you to start with if you are toying around with this. And of course, you don't actually know what they do. You can just kind of see, look, if this input comes, then it will kind of start attacking the big guy, and if this input comes, it will start attacking the small guy. Then we have another very interesting technology that I just want to show you before we run out of time. Genetic algorithms. Some of you were familiar with this, right? So this is actually where we get into an area where we can kind of have generative AI, where the AI can start becoming more complex. And basically it works just like our genetics. So I have the example here, you know, if we made a very tall, you know, creature with a kind of small but broad creature, we will have different mutants that come out of this, right? Which will be the offspring. And you can do the exact same for code, right? You can have different code elements that you combine. For example, you know, you can have a gene for aggressiveness and a gene for collecting food, for example. And then you can have different creatures with these genes, and when you breed them, they will have different permutations that will kind of live on in an ecosystem. And then you can start playing God and chopping off the ones you don't want with fitness functions and so on and so forth. And I'm going to show you an example of how that could be employed in a game. So here we have a small ecosystem. It's a swarm, and we have a lot of creatures running around. Look at that graphic, huh? Doesn't get any better. So the red ones are females and the blue ones are males, and the black one that's coming in there, which of course immediately ran out of the screen, is a beast with a very powerful set of genes. And basically what he's going to do is that he's going to start by killing off all the males, you know, just like a male lion, to ensure his own genes. And then he will start impregnating the females. And they're going to breed new creatures. Completely, you know, no control. We have no control. They will have, you know, a combination of different, oh shit, they all die of old age. I should probably give them a little more life, you know. We'll restart the simulation. God failed. God damn. Okay, so let's see whether I have more luck this time, you know. The previous one was the dinosaurs, and now it's the humans, you know. And basically the thing is here that you're breeding these creatures. I mean, I'm not very good at visualizing this, but basically the stars you see next to them are their genes. And they will have a completely different set of genes for each generation. And they can be different things like, you know, hit points or speed or, you know, longevity or whatever. And, you know, you just have an ecosystem breeding itself. And I've seen people kind of, you know, starting making arms and legs and, you know, like insects and kind of run around. And this, of course, gives completely new kind of ways that you can build games, right? You can have creatures breeding with each other, or you can have, you know, landscapes or levels kind of using these kind of magic things. Now, the last thing I want to show you, why I'm rushing this a little, is because you can actually combine those two things. You can combine the idea of having these kind of evolutionary genetics in code with neural networks. And that's a completely new paradigm that's coming up here, which is called neuroevolution. And as I mentioned a little in the beginning, what you do here is that you basically breed the neural network. So it becomes bigger, and it grows to the size where it can handle the complexity of the problem you throw at it. And before we run out of time, I'm going to show you a short example about how that works in practice. This is kind of cutting-edge technology. Okay. So here we have a robot, and now I'm gonna spawn 64 of them, and I want them to evolve their brain so they can stand up. And let's see how they manage. Oh, sorry, 16. So these are. Can you see them? I mean, they might be a little small for the guys on the last row. But basically what they're doing now is for each generation, they're becoming more complex, right? They're starting to twitch a little like zombies, you know? And basically what I'm telling them is, look, if you grow a mutation in your brain that enables you to stand up better than the generation before, keep that mutation in the population. If not, you know, we're gonna prune you. I don't know where you can see it, but they kind of slowly start rising, right? And we're not teaching them that. We're just telling them, look, stand up. You know, these are rigid bodies with kind of, you know, neurons attached to their muscles and so on. But we don't tell them how. They have to figure that out themselves. There's a question down here on the back row.
Are you planning to offer the source code with
Could you
your
speak
tools?
into the mic,
Yes.
sorry?
Are you planning to offer the source code along with these tools? When you...
Yeah, yeah, of course. Yeah, absolutely. Please, there's another question here, over here.
Yeah, what is the selection function for that?
What is the what, sorry?
The selection function for the new generation?
So the fitness function?
Yeah.
So basically what we did was that we gave them 2 points in the hip and the head. And then it's a combination of those. In the beginning, we just gave them the head, but it was too difficult for them to figure out because they first have like babies to roll on their back and kind of twitch. So first we wanted them to kind of raise their body, and we use the midpoint. You can also do all kind of averages to a certain extent, and then to kind of really get the maximum fitness, they have to pull their head up as well, right?
So why? But basically like height, like the higher they are, the better they are.
That's the idea, and this is also to kind of show some of the challenges, because the idea is that, you know, since you have gravity, the way your head can become highest is that you're actually standing on 2 feet. But you see all kinds of crazy strategies. Sometimes they start jumping or twitching an arm up or something like that, you know?
That's right.
And after a while, those mutations will kind of be weeded out of the population, but it also shows this kind of creative aspect, that they can do crazy things. I mean, we've done kind of hide and seek games, for example, where, you know, the AI has to hide for the player, and sometimes, you know, they develop crazy strategies like running around the player and standing there. So when you turn around, you know, the AI is kind of, and you have no control over it, but that's also the magic of it, that it will evolve until it's complex enough to solve the problem in some kind of magic way, right?
Awesome.
Cool. So.
You've got another question. You've got another question.
Oh, yeah, yeah.
Hi. I was wondering what kind of inputs you used for the neural networks here.
Yeah, so what we give them is actually their position of the different limbs. And then I think also we give them the velocity of the rigid body that is attached to the limb. The thing is that with neural networks that you don't really know which of these inputs they really need. I mean, the only way is to kind of try and change it a little. But what you can do is that there's some optimization techniques where after a while you prune all the connections that are not very strong on a kind of basis that they might not be important. And that often, first of all, gives better performance and also gives you an idea about what inputs are not needed, right? But that's a problem with these kind of hyperparameters. So when we evolve these, the thing we still need to kind of decide upon is what are the inputs, what are the outputs, and everything in between will be evolved. But of course, if you give it the wrong input, it won't learn, and you don't know. That's the kind of the problem. That's where you get to be God a little. Sometimes you're not very good at it, I must say. But you know, those are kind of the hyperparameters you still need, right? Yeah.
Okay, if it's they learn something from themselves, it's okay. But can they learn from each other and learn each other's behaviors to evolve faster?
That would be fantastic. I mean, this is one of the hard problems in any kind of neural computing right now. It was actually what is being discussed on the kind of state of the art, right? That is, how do we transfer learning between networks and between individuals? I mean, there is a little learning in the genes, you can say, that kind of, you know, when you get a new set of genes, you combine them, so they actually get some genes from each other, the next generation. But AIs between generations, no. There's no learning, there's no connection. And it's one of those problems that if we can solve that, it's either going to be fantastic or really scary for humanity, right?
Hi.
Hi.
Those sorts of evolutionary systems, like genetic algorithms, they are known to take some time to be trained, like many generations of on time. So is it already possible to use online training inside the game? That means that the AI is not just embedded, but they can learn while the player is using the game, so they can learn based on player actions, for example.
Yes, it is, but not to a very large scale. I mean, still, learning is so process intensive that you normally want to do it offline. But you can, for example, you can use player input and then do it offline and feed it back into the game. That's one way of doing it. And you can also do some learning inside the game, but then you have to kind of do it on other threads or stuff like that because it is quite intensive. Still the most popular way of doing it is to do it online, and then you kind of compress the network into some kind of array and throw it back, and then it can execute very quickly. Normally quicker than any other AI technology because it's just a bunch of floats that you kind of throw stuff into. Right? So I think it answers your question. Normally, we haven't seen a lot of applications where you use it in-game as such, real-time, runtime. Normally, you take out data, do it offline in some way or in parallel, and then you feed it back in. Okay, so we're kind of at the end here. We have exactly 27 seconds left. And we've had a lot of questions. There are some links here if you want to download some of the stuff we have. To articles and the projects and so on and so forth. And we have a booth out here, so if you have more questions, just come down and poke us and throw stuff at us and so on. Yeah, so thank you very much for having you.